Good morning. Thank you for coming to my talk. My name is Erin Sheridan. I am a graduate student with the Levy Group at the University of Pittsburgh, and today I'm going to talk about our work on nonlinear optical spectroscopy of graphene nanoribbons. Before I begin, I would like to thank our collaborators at the University of Nebraska-Lincoln and the University of Wisconsin-Madison, and also the funding agencies that have made this work possible. One of our goals in the Levy Lab is the development and utilization of a molecular scale nonlinear optical spectroscopy platform so that we can interrogate individual molecule-sized objects separated out from their ensembles. So that way we can further probe and manipulate their optical properties. And we do this using the lanthanum aluminate strontium titanate, or LAO-STO heterostructure. This complex oxide heterostructure has a wealth of interesting physical properties, but what's relevant here is the thickness-dependent metal-insulator transition that occurs at the interface. And there are fewer than 3 unit cells of LAO grown on top of STO. The interface is insulating, as you can see here. But when there are greater than 3 unit cells, the interface becomes conducting. There's this metal-insulator transition, and a two-dimensional electron system forms. Now, when the LAO is grown at exactly the critical thickness on top of STO, one can reversibly tune the metal-insulator transition. Here, for example, a backgate is applied to the bottom of the sample, and the polarity of the voltage applied is changed, switching between insulating and conducting. In our group, we developed a method to locally modulate this metal-insulator transition, and that is conductive atomic force microscope lithography, or CAFM lithography, and it works something like this. We start with LAO grown on top of STO at the critical thickness, and then we pattern contacts, and they have contact to the interface. We then bring a conductive AFM tip into contact with the surface of the LAO. When we apply a positive voltage to the AFM tip, it effectively deposits protons on the surface of the LAO. These in turn attract electrons to the interface, modulating this metal-insulator transition at the nanoscale. Likewise, if we apply a negative voltage to this tip, we're able to erase the conducting nanostructures that we created. Using this method, we've been able to create nanostructures as small as 2 nanometers in size at room temperature. And that leads me to liken this to an Etch-a-Sketch, but at the nanoscale. Using this lithography method, we can create a whole class of nanoscale devices. And here I'll focus on this nanoscale terahertz generator and detector. So as you can see here on the right, this device consists of a conducting nanowire drawn between a source and a drain electrode. And then there is a 10 nanometer insulating gap that is created in the nanowire. This is the site of our nanojunction. And we also connect to 2 voltage sensing leads. And what we're going to do, as pictured here on the left, is we are going to measure the photovoltage generated between V plus and V minus when ultrafast pulses are incident on the nanojunction. So we're going to apply a DC bias, VSD, across the nanojunction and measure delta V as a function of this time delay tau between 2 input pulses. So it's a bit mysterious. How does this very simple 4-terminal device actually generate and detect terahertz emission? And that is thanks to the third order nonlinear process. Strontium titanate, the bottom material of this heterostructure, has a very large third order nonlinear susceptibility. So heuristically, the process goes like this. We have a DC field applied across the nanojunctions that's highly confined in space to about 10 nanometers, and that gets multiplied into femtosecond optical fields, so these are highly confined in time. When they're multiplied together, we get this nonlinear polarization as a function of the difference frequency of these optical fields, and it's highly confined in both space and in time. Here is pictured the experimental setup that we use to perform our time domain spectroscopy. So first, ultrafast pulses leave our TAS Sapphire oscillator, and you can see the spectrum here. Then they enter our home-built pulse shaper. After that, they enter our home-built Michelson interferometer. So in this interferometer, there is a 50-50 beam splitter. And in the upper arm, there's a delay line, and that's comprised of a mirror mounted to a piezo stage. And this delay line is going to apply a time delay tau between the pulses from the upper arm and the pulses from the back arm. These two beams are recombined at the same beam splitter and then focused using a 100x objective onto the nanojunction. We are then, as I mentioned before, going to apply a DC bias from source to drain and then measure the generated photovoltage delta V as a function of tau, the time delay between the two pulses. Here's a typical time delay signal. So the x-axis is the time delay between the two pulses, and the y-axis is the amplitude of our response. Usually we look at the corresponding power spectrum. So we take a fast Fourier transform, and here are typical regions of interest in this power spectrum. We have the linear response. That's the response of the junction at the input frequencies, which are in the visible to near infrared. And then we also have a difference frequency generated response in the terahertz range and a sum frequency generated response. Using these devices and this experimental setup, in the past we have demonstrated an ultra broadband terahertz generation and detection at the 10 nanometer scale. So pictured here on the left are results of two wave mixing experiments over a large frequency range. And in panel B, what you see is the linear response of the junction to the two input frequencies. And in panel C, which is the main result, we show that we're able to generate terahertz frequencies with over a 100 terahertz bandwidth. This is an extremely broadband, nonlinear response. So now that we've characterized this platform and really shown how powerful it is, we want to use it to perform nonlinear optical spectroscopy of different nanoscale objects of interest, such as gold plasmonic nanorods, semiconducting quantum dots, graphene nanoribbons, and even 2D graphene itself. So as a past example of work that we have done, to demonstrate the power of this platform, we drop cast gold plasmonic nanorods on the surface of the LAO. We can identify a single nanorod using the AFM, and then we design a custom 4-terminal nanojunction device around that single nanorod. And we show in this data in the right panel that the time domain signal and the power spectrum, the response of the nanojunction is coupled to that of the plasmonic nanorod. So when the input light is polarized along the plasmonic axis of the nanorod, we see an enhanced terahertz response. So again, these are coupled. And what I'm going to talk about today is our recent work with graphene nanoribbons. So we receive a graphene nanoribbon powder from the Sinisky group at the University of Nebraska-Lincoln. And here are the nanoribbons pictured on the right. So these are chevron-type GNRs, and they're different from other chevron-type nanoribbons because they have a reduced energy band gap of around 2 electron volts. We've developed a method to deposit these nanoribbons on the LAO surface. So we begin with an inkwell. So we place some of this GNR powder on a substrate. Here we use an LAO-STO substrate. And then we bring an AFM tip into contact with the inkwell. Then we scan the tip in contact mode to pick up some nanoribbons. We then move the tip to the desired surface, and then we scan in contact mode again. And when we do this, the tip sheds nanoclusters of nanoribbons. After we do that, as before, we can identify a single GNR nanocluster and then design our nanoscale device around it using CAFM lithography. So I do this to create these 4-terminal nanojunction devices and then perform time-domain optical spectroscopy on them. Using this method, we can deposit GNR nanoclusters as small as 1 to 2 nanoribbons in size, and the 3 clusters labeled here are about 10 GNRs in size. So here on the right, you can see a sample device designed around a nanocluster. So here is the main channel of the 4-terminal nanojunction. Here is a side gate nanowire that we're going to use to gate the nanoribbons. And here's the connection to the faraway electrodes. And zoomed in, you can see the nanojunction with the gap right around the nanocluster. So as a reminder, what we're going to do on our time domain spectroscopy is measure this delta V, the photovoltage, as a function of time delay tau. And you can see as we tune the side gate applied to the nanoribbon junction, we see the time domain signal evolve. So on the x-axis is time delay tau, and the y-axis is this delta V. When we look at the corresponding power spectra, we see some very interesting features. First, we see some gate-dependent extinction features in the visible to near infrared. We also see an extinction feature in the second harmonic response as well. Additionally, we see that there is a gate-tunable second harmonic response and also a third harmonic response from the nanoribbons. We can look at the gate dependence of the nonlinear response by plotting the integral of it versus gate, and these are shown here. And what's interesting to note is that the second and third harmonics are maximized when these extinction features appear. And the terahertz response, or the DFG response, matches that of the linear response. So if I flip back, you can see when these extinction features appear, the second and third harmonics are strongest. So for comparison, I'll briefly mention some work we did previously on graphene. Because graphene is less than a nanometer thick, we're able to perform CAFM lithography through the graphene and define these nanostructures beneath. So you can see here on the right, here is the graphene with this nanojunction defined below at the LAOS-TO interface. So similarly, we perform this time domain terahertz spectroscopy. And in the graphene, what we've seen previously is extinction features in the visible to near infrared. And also, if we integrate over the power spectra regions, we see that the nonlinearity of this device is also maximized near where this extinction feature appears. So we are seeing very similar behavior in these nanojunctions, in these nanoribbons, and also in the graphene. Here are two example extinction features, one in the GNRs and one in graphene. You see they're very similar in their gate-dependent and optical power-dependent behavior, and similar as well. So we have almost 100% extinction of visible to near infrared light. Now this is occurring in a region of the electromagnetic spectrum where graphene typically only absorbs about 2% of light, as shown in this famous manuscript here on the right. So how can there be such strong optical absorption? In the past, we've proposed an explanation in which in 2D planar graphene, the nanostructure is acting like a highly doped graphene nanoribbon or nanodisk-like structure. When we apply a 1 volt source drain bias across the device, that is confined to this 10 nanometer region. And that gives rise to an extremely large electric field locally defined directly beneath the graphene. So perhaps that could make the local region of the graphene act as if it's like a nanoribbon. So there are these confined structures. And in these confined structures, there could be high energy plasmons. And those plasmons could give rise to plasmon absorption and also an enhanced optical nonlinearity. So to summarize, the LAOS-TO interface provides a platform for narrowband, continuously tunable, nanometer scale terahertz spectroscopy, or more generally, nonlinear optical spectroscopy. We have used these devices to observe spectrally sharp, gate-tunable extinction features in graphene nanoribbons and in graphene. These features are accompanied by an enhanced nonlinear optical response. And our proposed explanation is that these confined nanostructures host high energy plasmons and plasmon absorption. So with that, I would like to thank you for your time and take any questions.